Hello! Today we'll take a look at experiment 1 together. I have a bag right here with all of the gear and stuff that we're going to need for this. Let's take a look at everything that is inside. We have a lamp right here. We have a box with LED lights. And we have a lamp stand. We can screw in the light bulb now. We have a protractor right here as well. A cord for keeping the distance, right? And a multimeter, and that's all we're going to need. We won't require anything else for this particular experiment. And now we'll get started together. To begin with our experiment, the first thing that we are going to need is the solar panel. We will just plug it in right over here. And then we are installing the protractor. To do that, we're going to loosen the screw right here. Then you need to insert the screw through the protractor. And then you want to make sure the protractor snaps into place right down here. So now it has clicked into place and we can see the angles. Alright, so the protractor has now been installed, and for the next step we'll position the lamp in the right place. We still need to connect the cables with the LED box, and then we can finally begin with the experiment. The red plug must go into the red socket and the black one into the black. Now we can plug in the lamp and switch it on. And we can already see the LEDs are lit up here, and we're turning the solar panel to 0 degrees so that it's horizontal. We can take a look right away. 2 lights are currently lit. And now we would like to find out how much electricity we can produce, depending on the tilt angle of the solar panel. That's why we can now slowly adjust the tilt angle here. Let's set it to 30 degrees, and we can already see it's getting a bit stronger. The third light is also slightly lit up. We'll now set it to 70 degrees. And we can see now the fourth LED is slowly beginning to shine. So the more upright the panel, the more electricity we are generating. And let's have a look when we tilt it 90 degrees. And now all 4 LEDs are actually glowing. Let's see what happens if we go even further in the other direction. We tilt to 130 degrees, and then we realize that at this point only 3 LEDs are lit up. And if we go further to 160 degrees, then there are only 2.5 lights shining. And when we tilt it to 180 degrees, or simply horizontally, then only 2 LEDs are glowing, like in the beginning. This means we are seeing at 90 degrees, we have the optimal tilt angle, when the PV panel faces the sun. This produces the most electricity in this experiment. When it's in a horizontal position, we will generate the least amount of electricity. So, we're going to examine now the relationship of the electric current that is being generated to the orbital angle of the sun. For this, we have our sun here, or rather the lamp. We can go ahead and switch it on. And now, as you can see, it's positioned at a right angle to the solar panel. But how exactly does the current change now if we, so to speak, simulate the sun's trajectory here? And that's something we can simply try out for ourselves. So what we'll do is we'll try to keep it at the very same distance, and then we can move the lamp around the PV panel and observe how the LED lights behave. And we see here it's getting weaker. Now the fourth light has turned off as we move further to the side. You can also try this on the other side. Here in the middle, it gets stronger again. And if you go on further ahead, then the LEDs become less bright again. This means that the more vertical the sun is, The more light hits the solar panel, the brighter the small LEDs light up. This means that more electricity is generated. For the next experiment, we'll now examine the power curve simulation throughout the day. That sounds complicated at first, but what does that actually mean? Actually, you see, throughout the year, the days are of different lengths. For example, in summer the days are longer and in winter shorter. The day of the winter solstice is the shortest day there is in the entire year. Now we'll find out the specific numbers for your own solar power system, and I'll show you how to do that step by step. First, we're going to need this measuring string. With it, we can always maintain a constant distance between the lamp and the solar panel. They are simple to install. To do that, we're going to remove the solar panel first and put the cord in right here, and then we simply put it right back inside again. Then we'll take the other side of the cord and wrap it around the lamp. And now we can see we maintain a constant distance. In addition, we need a multimeter for this experiment to measure the accurate values. And we still have to do the wiring for this. For that, we'll insert the black connector into the middle jack, into COM, and the red connector here into the right jack. Then we can still adjust this. We'll specifically set it to 200 milliamperes. This is how it looks. And we already see a value on the display, and the reason for that is that there is light on this room. This means that the PV panel is already generating electricity. In order to find out accurate values, we still need to adjust the inclination angle right here. And for that purpose, we have this protractor, because on the roof, the solar cells actually have an angle of 30 degrees. And since the sun's trajectory is flat in our experiment, we need to adjust for that as well. We can, however, already set it to 30 degrees. If the roof were right here, then the solar panels would be positioned like this. Then, here on the protractor, the angle is given as 18.5 degrees, so that we can compensate for the trajectory, because our sun travels horizontally here, and not up here. That's why we add these 18.5 degrees, and then we get 48.5 degrees, which we'll now set here. And now we will get the most accurate readings, so we can pretty much go ahead and try it out. Down here on the base plate in the rosette, we can see indicated the winter solstice. Right here is where the sun rises, and then over here the sun sets. And by moving our sun on this trajectory, we are able to simulate a complete day with the sun, and subsequently we can then measure all the relevant values. And then we'll note those values down. So now we're going to switch on our sun, and the solar panel is oriented towards the south because most of the sun comes from the south. And additionally, the cardinal directions are noted down here. So you see, our setup is really close to reality. So we position our sun here for the sunrise. To make this look even more realistic, I'm going to use a dark piece of paper, since when the sun is rising up, it doesn't have the entire surface of the sun visible, because on the horizon, only a small part of it is visible at the beginning. This means we can hold the paper right here in front to better simulate the sunrise. And then we can actually already start noting down the first values. What you can do is you always write them down at an interval of, for example, 20 degrees. But you can also, for instance, record the values with an interval of just 10 degrees. That's why we're going to write down the value from this position for the sunrise. It is marked here on the board with an arrow. And you can read that value from the multimeter. We'll note down the first value. And then we move our sun a bit further and the paper blocks less of the sunlight. That is because we can see more of its surface, as over time, the sun that is shining on the solar power system rises more and more above the horizon. And then we simply move the sun a few more degrees, one interval, and record the next measured value. And so we can then observe the whole trajectory of the sun throughout one day. And the values of the electricity that is produced, we can then read and note down. And we'll do that together now. And again, at our regular intervals, we note down the measured values that the multimeter displays. And then we see we're already getting closer to the sunset, and then we'll need our cover paper again. We are simulating the sunset, just like the sunrise, just to have more accurate values. And here, when the sun has almost set, we then measure our final value. Just like that, we were actually able to calculate the total amount of electricity that our solar panel produced on the day of the winter solstice. That's incredible, isn't it? All the amazing things you can find out. Pretty cool, right? So, what do we learn from this now? If we take all the values that we noted down in a table and plot them as a graph, we have the power curve. It generally looks something like this. During the summer months, the power curve appears both higher and wider. It looks like this. Because the sun is positioned higher in the sky during summer, we receive more electricity. Therefore, in the summer season, we are able to generate way more electricity than during the winter.